All right, good morning, everybody. Welcome back to your favorite class. Yes. All right, ME3005, best class ever. All right, a couple announcements. Just kind of what's happening this week. Homework number 2 due today, so hopefully you got that in. I hope for you. Someone got it to my mailbox at 9:59. Good for that person. All right, so that's that. I'm going to post another homework probably later today on 3D stress, which is kind of the notes that we have going on right now. Should be rather short homework. Okay. Okay. Then this week in the lab period, which will be either Tuesday or Thursday, at the beginning of the lab period, the final work we do. So you've all had individual meetings with me about your writing and things you can do to sort of spruce it up and make it sparkle. So do that and make it sparkle and get it to my mailbox by 10 o'clock the day that you have lab. All right. In lab this week, we're going to do the combined loading, or not combined loading. Did I write combined loading? No, curve beam and bending. Okay. In lab, we do curve beam and bending, which is requires a sort of a lecture, 50-minute lecture or so on the material. And then I'll have another video for you to watch. Again, I'll have a handout. It'll be very similar to the last one. So hopefully the last one was as smooth as it could be. I know it's not ideal getting in the lab and doing it yourself, kind of watching me on video, but it's the best that we can kind of do right now. So I'm trying to make it as simple and as streamlined as I can. All right. So that's going to be there for you, and you'll have 1 week to do this lab. No more rough drafts, no more none of that. All right. 1 week to write the lab, and then it'll be due 1 week from your lab time. Okay. Any questions about what we got going on this week in the chat? Okay, nothing. All right. Then let us do the thing. I hope you guys appreciated my meme today. It's a thermo meme, but funny anyways. All right. So we left off with sort of 3D stress at a point. And I've kind of made this analogy a couple times now, but 3D stress at a point can be represented by what we call the stress cube, which has all of your stress components on it. I'm going to try to sketch this quickly. You've seen this a few times now. Get the general idea. And you have your stress components that are coming off of this guy. Okay. So we can sort of slice through this stress cube to create an oblique surface. And that oblique surface is like this. I forget what we called it exactly. Tetrahedron. Where we have a normal coming off of this particular face, n, and we have a normal stress in this general direction, which we labeled as sigma n, and then we have shear stresses that also act on the face in two different directions, called them tau n t2 and tau n t1. All right, so every cut that we make on any sort of surface, we get a normal stress and two shear stresses. All right, sort of makes sense. So there we go. We came up with an equation. We derived an equation for that normal stress in terms of the stresses that we already knew and the angles that that normal coming off of the face makes with the x, y, and z axis. So the equation for that normal stress was something like sigma x times L squared plus sigma y times m squared plus sigma z times n squared plus 2 times tau x y L m plus 2 tau x z L n plus 2 tau y z m n. It's our normal stress. And then we also defined what is the maximum shear stress on that oblique surface. And then we had the maximum shear stress, which is sort of this complicated equation, sometimes called the octahedral shear stress. It looks something like this. Sigma x squared L squared plus sigma y squared m squared plus sigma z squared n squared minus this quantity sigma x L squared plus sigma y m squared plus sigma z n squared to the 1/2. Sorry, that's squared. And then all of this to the 1/2. All right. So that was your max shear stress, also sometimes called the octahedral shear stress, for reasons we went into last lecture. Okay, so this is about where we left off last time. And we were in the midst of making the analogy between what we did in 2D and what we did in 3D to find the appropriate rotation of our element to get us into coordinates of maximum stress, specifically maximum normal stress, right? In 2D, we did this by taking the derivative with respect to the variable theta, which is this rotation angle for our two-dimensional square. In 3D, we're going to take the gradient with respect to the three angle variables that we have, which is theta x, theta y, and theta z. So if you remember in these equations, these variables here, L, M, and N, cosine theta x, M cosine theta y, and N is cosine theta z, where theta x, theta y, and theta z are the angular measurements between the normal axis coming off of our cut face and the principal or the original coordinate system XYZ that we had, right? So now what we're going to do today is we're going to look at how to get maximum normal stress by rotating our cube, what angles are required for that, and what the equation is for that maximum normal stress might be. Okay, so let's talk about that. So today, principal stresses. (3D). Okay. So recall in 2D, we had something that looked like this. Okay. And we could rotate this two-dimensional element into some other configuration through an angle of theta. Specifically, we can rotate into configuration to maximize sigma n through rotation angle theta p, where we said that theta p is 1/2 of tangent inverse of 2 tau xy over sigma x minus sigma y. All right. We found this by setting derivative of sigma n equal to 0. Hopefully we all remember this, okay? We're going to do a similar thing here in 3D. Right? Now in 3D, we're not going to take a two-dimensional derivative for this three-dimensional equation. We're going to take a three-dimensional derivative, okay? So in 3D, we follow a similar procedure, all right? We'll say in 2D, sigma n was function of only one variable, and that was theta. Or if we have the 3D analogy, what we're now calling like theta x, okay? Similar idea, right? Now in 3D, our sigma n is no longer just a function of one theta. We have three thetas, sigma x, sigma y, and sigma z. You can consider it as sigma x, sorry, not sigma x, theta x, theta y, theta z. Or you may consider it in terms of the directional cosines L, M, and N. It's basically the same thing, only separated by sort of a transformation from the cosine of each one of these angles. Okay. So if we want to find the maximum and minimum of this function, we want to find what variables, what values of theta x, theta y, and theta z would give you a maximum sigma n or a minimum sigma n. So we want combinations of theta x, theta y, theta z, which maximize or minimize theta n. Right? So to do this, we take the three-dimensional derivative, set it equal to 0, and determine what values of theta x, theta y, and theta z satisfy that condition. Okay, so take the three-dimensional derivative, which is the gradient of sigma n, and set to 0. All right. So what we want is, don't be scared, we're going to start putting some three-dimensional math symbols up here. We want the del sigma n. All right, brush your shoulders off from Calc 4, all right? Brush them shoulders off. We want grad of sigma n, which if you recall, is the partial derivative of sigma n with respect to theta x in the I hat, plus partial derivative of sigma n with respect to theta y and j hat, plus partial derivative of sigma n with respect to theta z in the k hat. All this equal to 0. This is what we want to do. It looks scary, but it's really not that scary. All right. So remember, your equation for sigma n in 3D is like sigma x cosine squared theta x plus sigma y cosine squared theta y plus sigma z cosine squared theta z plus 2 tau x y L times M, which is cosine theta x cosine theta y, plus 2 tau x z cosine theta x cosine theta z, plus 2 tau yz cosine theta y cosine theta z, right? This is the longer form. Instead of writing L, M, and N, we put in cosine theta x, cosine theta y, cosine theta z. So if I want the partial derivative of this with respect to theta x, it's not that hard, okay? You can do this, right? If you wanted to see one example of how this might be done, okay? Well, partial theta n, partial theta x. This term has a theta x. This term has a theta x. This term has a theta x. The other three don't have theta x's, so that's nice. We can just get rid of the other ones straight away. And we can just look at what happens with each one of these terms. All right, well, these are not difficult derivatives, all right? So the derivative of theta x, or sigma x cosine squared theta x, this is just going to be sigma x times negative 2 sine theta x cosine theta x. This derivative is not difficult, okay? If I look at this sort of second term here with the tau xy, I only have one term there that has a theta x. The derivative of cosine theta x is negative sine theta x. So here this will be minus 2 tau x y sine theta x cosine theta y. Right? Similar looking result for this term there. Be minus 2 tau x z sine theta z. Sorry, sine theta x cosine theta z. All this is going to be equal to 0. Okay, that is an example of sort of this first portion of the gradient that we would need to be on our way to solve this, right? So this term here, for instance, this guy, partial sigma n, partial theta x, would feed back into there, right? And so for this entire thing to be equal to 0, that first term must be 0, right? So this term here must all be equal to 0, as I've sort of written. Right? This equation has three unknowns to us: theta x, theta y, theta z. Right? We could replicate what we've done here with like partial sigma n, partial theta y, partial sigma n, partial theta z. We'd have two more additional equations. That would give us three equations and three unknowns, right? Three equations being these three partial derivatives, and the three unknowns being sigma x, sigma y, and or theta x, theta y, and theta z. So could replicate for partial theta n, partial, I keep saying theta, partial sigma n, partial theta y equals 0, and partial sigma n, partial theta z equals 0. We'll get three equations and three unknowns, where your unknowns will be theta x, theta y, and theta z. So if you solve that gradient, those three equations together, you will get theta x, theta y, and theta z, which give you the rotation angles to point you to the maximum and minimum normal stress, right? So these are I'll call them rotation coordinates. which give max and min normal stress. Capiche? Anyone crying yet? I'm crying on the inside. 3D math is hard. All right. Now we know from our two-dimensional analysis that we had two different rotation angles that could get us a condition of maximum or minimum stress. In 3D, what we have now, we have 6 possible combinations of theta x, theta y, and theta z that might give us a maximum or a minimum, local maximum or local minimum, normal stress. Okay. Interestingly, 3 of these are redundant because it would be like a slice through our 3D prism and a normal coming off of this way, or a slice through the prism and the normal coming off what would be like 180 degrees from that. Okay? So 3 of these are redundant. And the example here would be like visual example would be if you had like this tetrahedron here. It has a normal coming off of it. You have these angles here. You like theta y. Here you have the angle here that is theta x. And you have this angle here that is theta z. Okay. So let's say that those 3 coordinates, theta x, theta y, and theta z, gave you a maximum normal stress. There is also the ability to cut the sky such that your normal is not facing that direction, but the other way from your cut. So maybe that's kind of this like downward direction here, that you might call n prime, for instance. That has associated rotations, theta z prime. Maybe this angle here, theta x prime. And this one's going to be more difficult here. It's getting a little busy, I understand, it's theta y prime. Right. So x, theta y, theta z, redundant with theta x prime, theta y prime, theta z prime. Okay, it's the same surface, right, in both situations. All right, so because of that, there are 3 non-trivial, unique sets of theta x, theta y, and theta z, which when plugged back into your normal stress equation, will give you a minimum or maximum normal stress. 3 non-trivial, unique sets, theta x, theta y, z, which I'll put back into your normal stress equation, give max and min normal stresses. We call these max and min normal stresses principal stresses. All right. Now, I'll say that the math behind calculating those theta x, theta y, theta z triplets, plugging that back into sigma n and calculating the general equation for sigma n, that's way more algebra than what we want to do, okay? So we could come up with expressions like for this theta x, theta y, and theta z based on sort of those partial derivatives set equal to 0 that I sort of showed before, and take those sets of theta x, theta y, theta z, plug them back into sigma n, and come up with some expressions to give us the maximum and minimum normal stress. I'm just going to cut to the chase because that algebra is insane. Let's just say insane. So let's just say we figured out what those triplets are, the three unique triplets of theta x, theta y, theta z. Let's say we've carried them through in symbolic form and plugged them back into the equations for normal stress, sigma n, to get an expression for what our principal stress is. So I'll cut now to the chase. Back into sigma n, general form of principal stress. Oh, stress equations. Cutting to the chase, the final form. Actually, let's do this. I'll remind you, in 2D, this was the following. Okay, that's what it looked like in 2D. You have used this. If you turned in the homework and you did it on your own, suspicious. Just kidding. You use this equation. In 3D, it's the following. It's a cubic equation. Where we have what? What we'll say is sigma cubed minus. Leave yourself some space on the page. It's a long one. Caleb's getting mad. All right. Okay, I need more space. I would write this like on the whiteboard when I would do this like normal lecture, and I would write it across the whole board just for funsies. Okay, it's my favorite equation in the class. So what'd you say? It's not fun at all. You're not here for fun. You're here for learning. No fun. It's like Denzel Washington and Remember the Titans. Are you having fun? No. No fun, sir. Zero fun, sir. Exactly. There you go. Whew. This is a cubic equation in sigma. Exciting. Sigma 1, sigma 2, sigma 3, which are the principal stresses. To sort of simplify your life, this is often written in a simpler form, okay, which is a little easier to understand. Sigma cubed minus capital I1 sigma squared plus capital I2 sigma minus capital I3 equals 0. A little easier to see the cubic form if you write it in this fashion. And this is the fun one. Whew. Shake it out. Everyone shake it out. Let's go. These terms, I1, I2, and I3, are called the stress invariants. Okay? I'll write that. 1, I2, and I3 are known as the stress invariants. Spelling is hard. Invariant. That's because you'll notice here that these values of I1, I2, and I3 have no functional dependence on the angles theta x, theta y, and theta z. Okay? These values I1, I2, and I3 are always going to be the same regardless of how you cut your cube. All right? Always the same values. Interesting. So they're called the stress invariants. I think your equation sheet uses capital A, capital B, capital C. I have never seen that nomenclature in my life until I walked into this class and saw your general common equation sheet. Okay, so I didn't write the equation sheet for this class. It's common for all 3005 classes. And I guess the person who wrote the equation sheet likes capital A, capital B, capital C. I have never seen that written that way in any mechanics book ever. So sorry for that. I always see it as I1, I2, I3. There you go. So your equation sheet looks, your equation sheet has what is sigma cubed minus A sigma squared plus B sigma minus C equals 0. So your equation sheet has. All right, just so you're aware of that. Same equation, same idea. Okay. Good things. So once you solve this, this is a cubic equation. Principal stresses sigma 1, sigma 2, and sigma 3. Right? Sort of by convention, after you solve that cubic equation, we label those stresses sigma 1, sigma 2, sigma 3 from greatest to least. So your cubic equation is going to spit out whatever it spits out, 3 numbers. And just by nomenclature, these are generally labeled as sigma 1 greater than sigma 2 greater than sigma 3. So by convention, we label sigma 1 greater than sigma 2 greater than sigma 3. It's just the way that it is done. Okay, so these are your principal stresses. We also know that there is a maximum shear stress condition, right? What we've solved for here so far is like the rotation of the cube to get you the maximum normal stress. Is there a rotation for a cube that could give us maximum shear stress or minimum shear stress? The answer is yes. And the procedure for calculating those things is very similar, okay? Except we don't take the derivative of the normal stress equation. We take the gradient of the max shear stress equation, all right? So very similar process to determine max min shear. Max, tau, max. Sounds strange. Accurate statement. Turns out this is actually pretty easy to calculate. Turns out. After all that rigmarole, which we're not going to do, you're welcome. You're welcome. You're welcome. You're welcome. You're welcome. That your max shear in all possible three-dimensional configurations of your stress element is simply sigma 1 minus sigma 3 on 2. Oh, you were like ready to write like a zillion line equation, weren't you? Weren't you? Yes, you were. Don't lie to me. If you've ordered your principal stresses accordingly. Don't lie to me. You were getting ready. You were doing your hand exercises. Gotta warm up for this long equation. Okay. All right. I want to do an example problem. I don't think we're going to have time to get through it, but I think we can get through a portion of it. Give you a second to copy, and then we'll start in. The normal stress on a plane, that reminds me of like the famed Denzel Washington movie, Snakes on a Plane. Clearly the best movie he ever made, obviously. Was it Denzel? No, Samuel L. Jackson. Sorry. Denzel, not Denzel. Samuel L. Jackson. It was Samuel L. Jackson, right? I'm sick of these blanking snakes on this blanking plane. Yeah. Samuel L. Jackson. Forget about The Negotiator, that movie, in which he was brilliant. Forget about, John Q, or was that Denzel Washington too? Man, I'm getting those two confused. No, his best movie, Snakes on a Plane. So we're going to determine the normal stress on the plane, just like he determined the snakes on the plane. So let's go. Let's give this a go. So given stress in the x direction, 14 ksi. Stress in the y direction, 12 ksi. And stress in the z direction, 10 ksi. As well as shear stresses, tau xy. Here's 8 ksi. Tau xz is going to be 6 ksi. And tau yz is negative 10 ksi. Also, we're given rotation angles to our normal plane. So we're told we're slicing through some three-dimensional element, and we create an outward normal from that that has the following angles. our angle of our normal with the x-axis, 61.3 degrees. Our angle with the normal and the y-axis, 53.1 degrees. And our angle with the z-axis, 50.2 degrees. It's all information we're given. So we want to find sigma n, which is the normal stress defined by the plane given with these angles. And the principal stresses, sigma 1, sigma 2, sigma 3, and the maximum shear stress that we could have. All right. So this first part here, we want to find the normal stress on a plane defined by these angles. So pictographically in your mind, you should have something like, here's your tetrahedron. X, Y, Z. Here's the normal coming off of that face. Here's N. Your angles between the x-axis, y-axis, and z-axis were given. So here the x-axis, this angle, is 61.3 degrees. This angle here between the normal and the y-axis, 53.1. Kind of hard to envision in 3D, but just take my word, I guess. And this is 50.2. We want to find the normal stress on this plane here. Okay, well, that's easily done with our general equation, which is sigma x all squared plus sigma y n squared plus sigma z versus m n squared plus 2 tau xy lm 2 z n plus 2 tau y z m n, where L equals cosine theta x, which here is cosine of your 61.3 degrees. So you can punch this into your calculator. You'll get a value which is 0.48. M is cosine theta y, which is the cosine of 53.1, which is 0.60. And n is cosine theta z. It's going to be cosine of that 50.2 degrees, which is going to be 0.64. All right, so in our normal stress equation, everything is known. Right? There are no unknowns in this equation up here. So you just plug everything in and don't mess up, okay? On your calculator, just don't mess up. All right, so sigma n, after all of your punching, boop, boop, beep, beep, boop, boop, 12.3 ks. We'll stop here, and we'll calculate the principal stresses on Wednesday. And we'll be done with 3D stress at a point. Yay! Yeah, work it out, Caleb, work it.